Hello, my name is Candace Ward, and this video will introduce you to the fascinating physics of lenses and mirrors. We have a lot of material to cover, but don't worry. Optics is a pretty amazing topic, so we'll have fun. We'll explore the behavior of light by discovering how mirrors reflect light and how lenses refract light. By the end of this video, you'll be able to predict the behavior of light when it interacts with lenses and mirrors. Additionally, we'll quantify these interactions so that you'll be able to answer questions like the one at the bottom of the screen, which asks us to analyze an optical system. Whenever light encounters a different medium, reflection occurs. Reflection is the rebounding of light waves at the boundary of a medium. Light waves that are reflected are not absorbed into the second medium. Instead, they bounce off the second medium and travel back through the first medium. The law of reflection states that the angle at which a light wave hits the second medium is the same angle at which it rebounds back into the first medium. These angles are measured from the normal, and typically on the MCAT, angles are labeled theta. Let's apply the concept of reflection to a situation you're familiar with. Mirrors. Just like we saw previously, when a light ray hits a second medium, it reflects back at that same angle. Here we have a plane mirror, whose surface is totally flat. Since we have a flat surface off of which our light rays reflect, the angle going in is the same as the angle coming out. So if we have another source of light where the light wave is parallel to the first object, the rays will be parallel after reflection as well. If we mentally extend out the rays behind the mirror, we are imagining virtual light rays. An image is where our mind sees the light rays converge, and depending on the mirror, the image may seem to be at a different distance than the object is. For plane mirrors, the image distance behind is equal to the object distance in front of the mirror. For example, if I hold my hand 5 inches away from a plane mirror, I'll see an image of my hand seemingly 5 inches behind the mirror. The reflected light ends up in front of the mirror. This gives us a virtual image. Our mind extrapolates the light rays going into the mirror, and we see an image as though it were behind the mirror. Now, when we talk about optics, we need to consider the type of image we get. There are two types of images, real and virtual. A real image is one where the actual light rays converge. A virtual image, like we have here on the screen, is where we have to extrapolate out the light rays into virtual rays to get an image. So the actual light rays do not converge when we get a virtual image. For plane mirrors, you will always get a virtual image. Those light rays will never actually converge, so you have to extend them behind the mirror to find your virtual image. Plane mirrors aren't the only type of mirrors, however. If you've ever looked into the curved inside of a spoon, you've been looking at a concave mirror. Concave mirrors are converging mirrors. To remember what a concave mirror looks like, think about how you're looking into a cave. If you look at the back of the spoon, you're looking at a convex mirror, which are diverging mirrors. Converging and diverging refer to whether the light rays will bounce off the mirror to come together or split apart. We'll cover that more in depth later. Concave and convex mirrors are types of spherical mirrors. If we imagine a complete sphere, which we'll indicate with a dotted line, our concave or convex mirror is merely a portion of that sphere. The C in the middle of our diagram stands for center of curvature, or the center of our sphere. The radius of the sphere is the distance from the center to the edge of our mirror. The F on our diagram stands for focal point. Now, there are several important lengths to consider when dealing with spherical mirrors. The distance between the focal point and the edge of the mirror is called the focal length. The focal length is equal to half of the radius. This fact is true for all spherical mirrors. For every optics problem, you'll have an object. This object is the source of the light waves. For spherical mirrors, the distance between the object's location and the mirror itself is an important length. This length is usually labeled O. Another important length in terms of spherical mirrors is the image location. Depending on the position of the object in relation to the focal point, the image can be found at a different distance from the object itself. The distance between the image location and the mirror is usually labeled I. Here is a really important equation for you to know for test day. Remember, F stands for focal length, O stands for object distance, and I stands for image distance. Given any two of the values of F, O, or I, we can calculate the third. For example, if we're told where an object is located and where its image ends up, we can calculate the focal length for that spherical mirror. Lucky for us, units don't matter as long as they're all the same. For instance, if we're given object distance and image distance in centimeters, we don't have to do any unit conversions. Our equation will just give us the focal length in centimeters as well. Here's some more information we can gather from image distances. When an image distance is greater than 0, we have a real image. We get a positive image distance for a mirror when the image appears in front of the mirror, where you'd expect it to be. When an image distance is less than 0, we have a virtual image. A negative image distance tells us that the image is behind the mirror. Now that we've got some basic optics terms under our belt, let's expand our knowledge by looking at magnification. Magnification is the negative ratio of the image distance to the object distance. One thing that this value gives us is information about the orientation of the image that the mirror produces. When we have a negative magnification, our image is inverted or flipped upside down. When we have a positive magnification, our image is upright in the same orientation as our original object. Don't forget about the negative sign in the magnification equation, or you could flip the orientation of the image. In addition to telling us the orientation of the image, magnification tells us whether the image that the mirror produces is bigger, smaller, or the same size as the original object. When we're trying to figure out the size of the image, we need to look at the absolute value of the magnification. When the absolute value of the magnification is less than 1, we get a reduced image. A reduced image is an image that is smaller than the original object. In contrast, a magnification that is greater than 1 gives us an enlarged image. Luckily, we don't always have to do calculations. Here's a trick for your MCAT. If the image distance is greater than the object distance, you'll get a magnified image. If the image is closer to the mirror than the object, you'll get a reduced image. We'll practice this concept in a bit to make sure you understand magnification. Let's try applying all of this new knowledge to a specific situation. Here we have a concave mirror. We know it's concave because we're looking into a cave. Now remember that concave mirrors are converging systems. These mirrors will cause our light rays to come together. In this case, our object is in between our center of curvature and our focal point. We're going to construct a ray diagram to figure out where our image will end up. The first thing you do is draw a line from the object to the mirror in a parallel line. This ray of light will reflect off the mirror and travel directly through the focal point, as you see in the diagram. The next line you draw will start at the object again and hit the mirror right where our main axis hits. It'll reflect off the mirror at the same angle as it goes in. Our image forms where these two light rays intersect, way out here to the left. Remembering our rules from earlier, if we have an image distance greater than 0, we have a real image. For mirrors, an image that's on the same side as the object is positive. The same goes for objects. An object that's on the same side as where the light's coming in is considered positive. If we think back to our magnification equation, we put our positive image distance on top, then divide it by our positive object distance, and then we put a negative sign in front of that. So our overall magnification is negative, which means that we have an inverted image. Finally, we have to think about the size of our image. We need to compare our image distance to our object distance. When we have an image distance that's greater than our object distance, we get a magnified image. So to sum up, when we have an object that's between the center of curvature and the focal point of a concave mirror, we get a real, inverted, magnified image. How about another situation? We have the same concave mirror as before, but now the object is located at our focal point. Just like before, we'll draw our first line parallel to the central axis, and it's reflected back through the focal point. The second line starts at the object, then contacts the mirror at the point of intersection between the mirror and the axis. Then it reflects off at the same angle. Uh-oh, our rays are parallel. Since parallel lines will never converge, we don't get an image at all when our object is at the focal point. Okay, one last concave mirror problem. Now our object is between the focal point and the mirror. Again, ray 1 is parallel to the axis, then reflects back through the focal point. Ray 2 reflects off the mirror at the point of intersection, and it has the same angle coming out as it does going in. This time, our lines are not parallel, but they're actually splitting apart. We won't ever see them converge on the left side of our mirror, but if we virtually extend them behind the mirror, we see that they converge on the right side. Let's go through our equations again to describe this image. Earlier we said that an image on the same side as the object is positive, but we have the opposite case here. So our image distance is negative, meaning that we have a virtual image. Now we have a negative image distance divided by a positive object distance, which gives us a negative value. And then we put a negative sign in front of that. So we actually get a positive magnification, which tells us that we have an upright image. And finally, we see that our image is again farther away from the mirror than our object, so we have an enlarged image once again. In summary, for this concave mirror, an object that is between the mirror and the focal point produces a virtual, upright, and magnified image. Let's try a diverging mirror system. Here we have a convex mirror. For convex mirrors, there are some conventions that we should be mindful of. If we're the person looking at this mirror, we're standing on the left side of the diagram. If we think about this mirror as a sphere, we're standing on the outside of the sphere looking at the outer surface. So it makes sense that the center of this sphere is going to be on the other side of us, just like we see in the diagram. For convex mirrors, the center of curvature and the focal point are on the other side of the mirror. Also, I mentioned that convex mirrors are diverging systems, which means that these mirrors split the rays apart instead of making them converge together. Keep that in mind as we draw out our ray diagram. Alright, we're all set to check out our ray diagram for convex mirrors. Let's just place our object here to the left of the mirror. The first ray will be drawn from the object parallel to the axis, then bounce off the mirror at a certain angle, which we'll get to in a second. The second ray will bounce off the mirror at the point of intersection and reflect at that same incident angle. Obviously, these rays will never converge on the left side of our mirror. So we'll extend our rays again, and we see that our image is behind the mirror, which we know tells us that it's virtual. If you look at the dashed green line, you'll see that it goes through the focal point. Earlier, I said that the first ray bounces off the mirror at a certain angle. This angle is the opposite of the angle that would take the ray through the focal point. We could go through all our equations to figure out the specifics of this image, but you just need to know this for the MCAT. An object in any location for a convex mirror will produce a virtual, upright, reduced image. Just think of the convex security mirrors you see in a convenience store, and that's exactly what's happening here. We've been dancing around these values for the past few problems, so let's create a chart that will help you keep track of when a length is positive or negative. This chart is specifically for mirrors. Things are a bit different for lenses, so we'll cover that later on. Earlier, I mentioned that an object that's on the same side as the origin of light is positive. So if an object is somehow on the opposite side of the light, it's negative. This is basically impossible for mirrors, so the majority of objects we'll deal with have positive object distances. We saw earlier that an image that's in front of a mirror has a positive sign, while an image that's behind the mirror has a negative sign. For mirrors, a positive image is a real image, while a negative image is a virtual image. Our radius of curvature is positive for concave mirrors and negative for convex mirrors. Same situation for focal point. What did we say earlier about positive and negative magnifications? A positive magnification indicates an upright image, while a negative magnification indicates an inverted image. These conventions are really important to know for test day. You'll need the right sign in order to properly use all the equations we've already analyzed. One last thing before we move on to an example. You may have noticed a pattern about the orientation and type of image. All of the inverted images we saw were real, and all of the upright images were virtual. You can remember this with the mnemonic IR and UV. For a positive object distance, inverted is real and upright is virtual. The fact that IR and UV, which should also make you think of infrared and ultraviolet light, are areas on the electromagnetic spectrum, should help you recall this mnemonic. Let's try an example together to incorporate all our knowledge about mirrors. Here's our problem. We're given a concave mirror with an object in between the radius and the mirror, and we need to solve all those values listed. Don't freak out. Let's just think back to our nice equation that related all these different distances. First, let's solve for image distance. Here we have our R value, but is it positive or negative? We're told we have a concave mirror, so we know that our R is going to be positive. Here's part of our equation now. The question stem also gives us our object distance, but we also need to determine whether it's negative or positive. Since we're told it's in front of the mirror, where the light is coming from, we have a positive object distance, and the rest of our equation looks like this. When we solve it out, we see this value, negative 1 over 30. Taking the inverse, we know that our image distance is negative 30 centimeters. The next value we're going to solve for is magnification. Pulling up our magnification equation, we plug in the values of our image distance and our object distance, and we get a dimensionless value of positive 6. Now we're asked to determine whether this image is real or virtual. We need to look at the sign of our image distance to determine this. A negative image distance tells us we have a virtual image. Lastly, we need to figure out the orientation of our image, and we look to the sign of our magnification to determine that. A positive magnification tells us that our image is upright. Whew, that took a lot of legwork, and I know it can seem overwhelming at first, but lots of practice will make this equation and the sign convention second nature.